Hey guys, welcome back to Quick Code. Today we're doing another Brainstellar Quant puzzle. This one is called Duck and Fox. I'll let you guys go over it. So just to draw out what is going on, we have a circular lake and the duck is currently at the center, and let's say the fox is over here at the perimeter. Now the fox is waiting at the shore of the lake and the fox is not able to swim, but the fox wants to eat the duck, right? So the fox will basically try to catch the duck as soon as it reaches the shore. The fox can move around the whole lake at a speed of 4 times the speed at which the duck can swim. So just to assign a few values, let's say the fox can go at a speed of 4v and the duck can go at a speed of v. The duck can fly, but only once it reaches the shore of the lake. It can't fly from the water directly. Can the duck always reach the shore without being eaten by the fox? And if it reaches the shore without being eaten by the fox, it can hence simply fly away instantly. No, this is an old duck and cannot take a flight while swimming. The duck cannot submerge in the water. So basically, the problem is that we've been asked that if this duck, and let's say the circular lake has a radius of r. So the problem is that can this duck somehow reach the circumference or the shore of the lake before the fox reaches that exact same position? And if the duck can, then it can even if it has like 1 millisecond before the fox reaches the duck can just fly away. So the question is, can the duck devise a strategy to reach the shore without the fox uh, being able to catch the duck? So I've also listed down a few more points just to clarify everything. So now we'll be going on to how to approach the solution. So in my opinion, the best way to tackle these kinds of problems is just to try to start thinking about random ways or random strategies the duck might try to attempt, like try to think of to escape the fox. So one initial strategy that might come to mind is the duck might simply just try to swim away in the opposite direction, right? Because that this point is the furthest away from the fox currently, and each point on the circumference would take the exact same amount of time for the duck. So it's just the best to go to the point that's the farthest from the fox, because that way the fox will take the maximum amount of time. So since this distance is r, and by math we know that half of the perimeter length is 3.14, which is basically an approximation for pi times r, and the duck speed is v while the fox's speed is 4v. So how much time does it take the fox? It takes you, time is distance upon velocity. So this comes out to be something looking like this, while the time for the duck comes out to be something looking like this, right? And you can see that this value is less than 1, which means this value is less than this value. So the time for the fox is less than the time it will take the duck, and hence the fox will already reach there by the time the duck reaches there, and the duck will have no other choice but to have been eaten, right? So another case that you might think of is, what if the duck tries to spiral its way out so that it's trying to maintain a 180-degree phase difference with the fox at all times, right? So um, this also doesn't work, because what starts to happen is, since the velocity of the fox is 4v and the duck's velocity is v, no matter how fast, no matter how small the radius of the duck is during the initial spirals, once it comes close to the shore, it has to be traveling at a radius of almost equal to r, right? And since they're like trying to circle around the same radius circles, and the duck has a velocity of 4v, it just won't be possible. And another point that might start to come to your mind is during the course of the duck trying to escape the fox, if at any point, let's say when the duck starts to venture out, if at any point radius r less than the initial ri, this is r, at this point, if the duck stops, then, well, the best strategy for the fox is to quickly come to the point that is closest to that position. So let's say the duck stops over here, and the fox will try to, as soon as possible, try to reach to this position, which is the closest to the duck. This is, each and every case is worse than the duck just being over here at the center and the fox being anywhere on the circumference. If the duck stops at any point that is not the center and the fox somehow reaches the point that is closest to that point on the shore, then it's just an even worse case. So coming to the real solution, and this kind of takes a bit of thinking, but strategy for the duck is, well, the duck can only really escape if it goes diametrically outwards, because that has the best bet, right? But the problem is, if it tries to do that from the very center, then there's just not enough time for it to reach the. So let's say the duck is over here, the fox is over here. If the duck tries to just ball out diametrically from the center, then it just doesn't work, right? Because we just calculated in our first case that the time for the fox is less. But if the duck somehow travels r/4 distance, maintaining a 180-degree phase shift with the fox, and if now let's say there's just 3r/4 length remaining, and the fox is over here. So now in this case, the time comes out to be, for the fox where this is the exact same, it's just 3.14 r/4v, right? But for the duck, now this comes out to be 3r/4 into v. And you can see that this fraction is less than this fraction. There's actually even more values, not just r/4, which will suffice this solution. But I've just taken this one for an example. So if the duck can reach a radius of r/4 and be diametrically opposite to the fox at all times, then it can just, at that point, diametrically, or radially just try to swim its way out and fly away as soon as it reaches the shore. Now, you might ask, okay, how does the duck reach a radius of r/4 while the fox is diametrically opposite to him? As soon as the duck will be trying to reach that small circle, the fox will start chasing it, right? Well, to answer this, we use the other case that we talked about where the duck was spiraling outwards. Now, if the radius is less than r/4, then the duck can successfully spiral out, maintaining the 180 degrees phase shift with the fox. Why do I say this? Well, I'll try to explain it over here. But I think you guys can imagine that for super small radiuses, it's like very easy to maintain a 180 degree phase shift. But as soon as the radius becomes larger and larger, it gets more difficult. But so it must be the most difficult when the radius is just about to be r/4, right? Well, if you do the calculations, since the perimeter for a r/4 radius circle is 2 into pi into r/4, that is the distance, and the velocity for the duck is obviously v. The fox, the perimeter is still 2 pi r, and the velocity is 4v. If you try to calculate the time it takes to do one full revolution for the fox, this comes out to be 2 pi r/4v, and for the duck, it comes out to be 2 pi r/4v. So it's the exact same amount of time. And for any circle slightly smaller than r by 4, the time for the duck will be less than the time for the fox. So basically, if the duck is spiraling a smaller circle of radius r by 4, or well, actually slightly less than r by 4, then the duck can maintain that 180 degrees phase shift with the fox at all times. And whenever it feels like it's close enough, it can just radially swim outward and then fly away. And I've also made a summary of this solution. Yeah, so here's the solution. This is actually the solution given on the Brainstellar website. It's basically summarizing whatever we talked about today. Thank you.